In this video, we're going to be looking at some of the ways we can classify chemical reactions. So chemical reactions can often be classified by either the types of reactants and products involved or by some pattern that occurs in the bonding. So understanding what kind of chemical reaction you're dealing with can often be important to understanding how it's going to happen, what types of conditions are going to make that reaction more favorable, or understanding how understanding what types of reactions particular types of chemicals are likely to do. Can help you predict what's going to happen when you mix things together. So if you mix two chemicals together, sometimes the reaction happens, sometimes it doesn't. And understanding some different types of reactions can often help you figure out, if I mix these two things together, is a reaction going to happen? Do I want that? Who knows? And what types of products are going to be produced. So just a quick note that there are many types of chemical reactions. There are many ways to classify things, and we're just talking about a few. Just to get a taste of what types of reactions are out there, sort of one way or a few ways that we can potentially classify reactions. Not every reaction you see is going to fit into one of these categories, and that's okay, but these are just some of the more common categories that are out there. So the first one that we're going to talk about, we're going to look at 5 types of reactions, is referred to as a synthesis. So this is when multiple reactants combine to form a smaller number of products. So, for instance, super generic representation of this could be A plus B forms C, that we're taking these two things, A and B, and we are combining them together to form one new different thing called C. An actual example of something like this would be magnesium reacting with oxygen gas to produce magnesium oxide. We are taking two different elements and we are combining them into a single substance. So synthesis reactions commonly have 2 reactants in one product, but it can be more complicated than that. We can have a larger number of reactants than 2. We can have a larger number of products than 1, but the general pattern is more stuff to less stuff, or more different things to fewer different things, I guess is the better way to put it. So sort of the opposite of synthesis is what we call decomposition. Which is when one or a few reactant molecules break down into a larger number of product molecules. And when you think of the word decomposition, you probably think more of the biological process of something decomposing after it dies, and that is a bunch of decomposition reactions. This is called decomposition for a reason. When a biological system decomposes, what is happening is all of those big complicated molecules, those macromolecules, the fats, the proteins, the complex carbohydrates are breaking down into smaller pieces. So you have a few really big molecules breaking down into all of their component amino acids and simple sugars and all of that good stuff. So it is a decomposition type reaction from the chemical standpoint. So sort of generic representation of this might be A reacts to form B and C. We're taking this one molecule A and we are splitting it apart into two separate things, B and C. A real world example would be hydrogen peroxide reacting to produce water and oxygen gas. So this one substance, H2O2, splits apart to become two different substances, water and oxygen gas. So these first two types of reactions are really all about like how many things do we have on each side is really the only pattern to them. Are we taking a bunch of stuff and making fewer things, or are we taking few things and making a bunch of stuff? But at least in theory, any kind of atom or molecule or compound can take place in either of these, or can take part in either of these. There's no restrictions on what kinds of compounds can be involved, unlike the next two we're going to talk about. So the next, I guess the rest of them, the next three, are all specific to particular types of reactants reacting and how they're likely to react, for lack of a better word, I guess. So the first one is known as a single replacement reaction. Sometimes single displacement, either one is fine by me. I usually use replacement, it's just what I learned. So this is when a pure element reacts with an ionic compound. So here we are specifying what types of reactants we need to have. That we need to have one thing that is an element, and we need to have one thing that is an ionic compound reacting together. And what is going to happen is that the element trades places with one of the ions. Knowing which one is going to get replaced kind of depends on what your element is. So metals, metallic elements, will replace the cation, which should also be a metal, and non-metallic elements will replace the anion, which should also be a nonmetal. And what we get as a result, my element is taking the place of one of the ions, is that we get a new element, the new ionic compound produced. So, generic example. Might look something like this. Actually make this. M is a commonly used just symbol for generic metal. So that makes sense here. So what we are doing is if this element, this one element by itself, is a metal, that means it's going to trade places with my cation, because metals always form positive charges when they form an ion. So the metal and the cation are going to swap places. So that means that whatever was the cation in my ionic compound is now going to become an element by itself, and the thing that was an element is going to become the cation in my new ionic compound. So for an actual example, we might have zinc react with silver nitrate. When these two things swap places, the silver is now going to be by itself in its elemental form, and the zinc is going to become part of the ionic compound as zinc nitrate. So we can see this sort of one thing replaces another is where the single replacement name of this type of reaction is coming from. The next one is known as double replacement. And this is when two ionic compounds react together. And what happens, the change that occurs, I like to think of as the ion swapping partners. And two new ionic compounds are produced as a result. So we'll see what swap partners means in a sec. So if we have two ionic compounds, let's call them AX and BY. When my ions swap partners, I'm just going to take my cations and swap them between the two compounds. You can think of it as switching anions if that's easier for you for some reason, but you always want to make sure that you are exchanging either a cation with a cation or an anion with an anion, because in order for something to be a valid ionic compound, you have to end up with one cation and one anion in your formula. So there's only one valid way to switch things around. That if I'm gonna take the cation out of this formula and trade it in for something else, I have to trade a cation for another cation. I can't end up with two anions paired together because two negatively charged things would repel one another, which is no good. So I usually think of it as my cation swapping places. So A was originally paired with X and B was originally paired with Y. In my products, I'm going to end up with B paired with X and A paired with Y. So I've just swapped where my which anion my cation is paired with. An actual example of this might be lead nitrate reacting with sodium chloride. And when this occurs, if I swap my cations here, the sodium is going to end up paired with the nitrate. So I will have sodium nitrate as one of my two products. And then the lead is going to end up paired with the chloride, so lead 2 chloride would be my other product of this reaction. And then last but not least, we have combustion. So combustion is very specific in what types of things it involves. It needs to have some kind of carbon-based compound as one of the reactants, and that reacts specifically with oxygen gas. To produce water, and carbon dioxide. So it is very, very specific in the reactants and products. The only thing that has any variance is what is the carbon-based compound. But other than that, you have something involving carbon reacting with oxygen to produce carbon dioxide and water, specifically as your products. So there's no good way to do a generic example of this, so I'll just give a real one. We have C2H, I missed a thing, C2H4, apologies. C2H4 is my carbon-based compound reacting with oxygen gas to produce carbon dioxide gas and water. So again, what is this compound is the only thing that really varies here, but it will always involve some carbon. Generally, it's going to be, for the purposes of this course anyways, a hydrocarbon, which just means something that contains carbon and hydrogen and nothing else. You can combust other things, but the reactions sometimes get a little bit more complicated, but still fundamentally the same thing. So these are just a few of the different ways that chemical reactions can be classified to help us understand sort of how they're going to work.